In this video, we continue solving problems related to the concepts in Chapter 10. Here we will focus on valence shell electron pair repulsion theory for predicting molecular structures. VSEPR is used to predict three-dimensional structures of molecules based on the principle that each group of valence electrons around a central atom is located as far as possible from the other electron groups in order to minimize repulsions. A group of electrons is either a single bond, a double bond, a triple bond, a lone pair of electrons, or a free radical electron. The steps that we follow to develop this molecular shape are shown here. We take our molecular formula from which we deduce a Lewis structure where we count the number of electron groups around the central atom we're considering, and that gives us an electron group arrangement in our classification scheme. And based on that, we count up the number of known lone pair electrons from which we deduce a molecular shape. There are 5 primary electron group arrangements that we will see for main group elements, particularly the ones that we'll look at. And these include the following. For 2 electron groups, we have a linear electron group arrangement. For 3 electron groups, we have a trigonal planar electron group arrangement. For 4 electron groups, we have a tetrahedral electron group arrangement. For 5 electron groups, we have a trigonal bipyramidal electron group arrangement. And for 6 electron groups, we have an octahedral electron group arrangement. For the linear electron group arrangement, we only have one molecular shape or molecular structure, and that is linear. For the trigonal planar electron group arrangement, that is when we have 3 electron groups, we can have 2 different molecular shapes. One is a trigonal planar molecular structure, or for one lone pair, then we will have a V-shaped molecular structure. For a tetrahedral electron group arrangement, we can have either a tetrahedral molecular structure, or if we have one lone pair, we can have a trigonal pyramidal molecular structure. Or for 2 lone pairs, we can have a V-shaped molecular structure. If we have 5 electron groups for a trigonal bipyramidal electron group arrangement, the molecular shape can be trigonal bipyramidal, seesaw if we have 1 lone pair, T-shaped when there are 2 lone pairs, or linear in those cases where there are 3 lone pairs around the central atom. For an octahedral electron group arrangement, where we have 6 electron groups, the molecular shape can be octahedral or square pyramidal for 1 lone pair, or a square planar molecular structure when we have 2 lone pairs. We're going to go through and look at the Lewis dot structures we generated in our previous video and see what the predicted molecular shape is based on VSEPR. We'll start off with oxygen difluoride. Oxygen is the central atom. You can count up electron groups around that central atom, and you should come up with 4. That's the number of electron groups around the central atom. That's from 2 lone pairs and 2 single bonds. With 4 electron groups around the central atom, the electron group arrangement about the central atom is tetrahedral. And the molecular shape that we deduce then for a system that has 2 lone pairs around the central atom And a tetrahedral electron group arrangement around the central atom is a V-shaped molecular structure. Next, we look at H2CO3, that is carbonic acid. Carbonic acid has three central atoms. There's the carbon central atom, and then there's the two oxygens that each have one hydrogen attached to them. They're central atoms as well, so there'll be a shape around all three of those atoms. Let's start off and look at the carbon atom first. If you look at the carbon atom, how many electron groups do you see? You should see 3 electron groups. There's one single bond, there's a second single bond, and then there's a double bond. The double bond is one electron group, and each of the single bonds is an electron group. So that the electron group arrangement around the central carbon atom now is trigonal planar. The molecule then has a shape that's defined by this. We have no lone pairs, a trigonal planar electron group arrangement. So we have a trigonal planar molecular structure about the carbon atom. And indeed, the molecule is flat about the central carbon atom. Now, the bond angles are not 120 degrees because one of the oxygens is doubly bonded. Therefore, the oxygens, which have hydrogens attached, form an oxygen to carbon-oxygen bond, which is less than 120 degrees. The oxygen that's doubly bonded will form an oxygen-carbon-oxygen bond angle that's greater than 120 degrees. Next, we can look at the oxygen atoms. So if we take one of the oxygen atoms with a hydrogen atom on it, you can count the number of electron groups around there. You should come up with 4, 2 lone pairs, and 2 single bonds. That tells us that the electron group arrangement about the central oxygen atoms, in this case, since there are 2 of them, they're both tetrahedral. The molecular shape about the oxygen then, with 2 lone pairs and a tetrahedral electron group arrangement, gives us a V-shaped molecular structure about the oxygen atom. Next, we see the nitroxyl molecule, HNO. We can look at the central nitrogen atom. So if we look at that nitrogen atom, we can ask how many electron groups are around that nitrogen atom. You should come up with 3. There's a single bond, there's a double bond, and there's a lone pair. 3 electron groups tell us that our electron group arrangement about the central nitrogen atom is trigonal planar. For a trigonal planar electron group arrangement with 1 lone pair, the molecular shape then is V-shaped or bent. Next up, we have the ammonium ion, NH4+. We can look at the shape about the central nitrogen atom. There are 4 electron groups around the central nitrogen atom, 1 for each nitrogen-hydrogen bond. For 4 electron groups, the electron group arrangement about the central nitrogen atom then is tetrahedral. The molecular shape is deduced by considering that we have 0 lone pairs and a tetrahedral electron group arrangement. Therefore, the molecular shape is tetrahedral. And the bond angles in this case are 109.5. All of the atoms are identical. Next, we'll look at the bisulfite ion. The monohydrogen sulfate anion has a resonance structure that's shown here. If we look at the central sulfur atom, you can count up the number of electron groups. How many do you see? You should come up with 4 electron groups around the central atom. There'll be a lone pair, a double bond, and 2 single bonds. Now there are 2 different resonance structures, but they'll both give you the same number of electron groups around the central atom. That's important. So the electron group arrangement about the central atom is tetrahedral for 4 electron groups. From this, we can deduce a molecular shape. We know that we have 1 lone pair and then 3 groups of bonds. So we have 1 lone pair, a tetrahedral electron group arrangement. The molecular structure is trigonal pyramidal. And in fact, that's what we see. The last molecule we'll look at is iodine trifluoride. The Lewis dot structure is shown here. The central atom is iodine. We can go through and count up electron groups. So see how many you get. In this case, you should get 5 electron groups around the central atom, 3 single bonds, and 2 lone pairs. For 5 electron groups, the electron group arrangement about the central iodine atom is trigonal bipyramidal. For a trigonal bipyramidal structure with 2 lone pairs, the molecular structure is T-shaped. That concludes Chapter 10. In the next video, we move on to Chapter 11.